The goal for today is we're going to talk about a different type of problem that we can solve. It's called a first-order differential equation, which is linear. So a linear first-order differential equation. And what does that mean? Well, it's what it says right here. You can write it as y prime plus p of xy equals q of x. Now, this word linear will show up from time to time in mathematics, and it seems like mathematicians really love things which are linear, and it's true. We really do love things which are linear. And so you might say, well, what does it really mean to be linear? Well, it turns out that this word linear basically boils down to two ideas. It says you can add stuff, and the other thing is you can do what we call a scalar multiply. In other words, multiply by a, if I can spell correctly, multiply by like a constant. So that's what we mean when we say something is linear. And so here what we're doing is when we say that this is linear, what we're really saying is if you look at the y part, you have just a y prime piece and a y piece. And so we have multiples in front, but what is in front doesn't depend on y. And so it's a linear combination of y prime and y, meaning that there's something times y prime plus something times y, and that's the idea. Now these are very nice, and they do show up in pretty intuitive settings, actually. We'll see an example here as we go along. And there's a nice fact here, which says if we have a first-order linear equation of this form with some initial values, then as long as p of x and q of x are nice, here nice being continuous, then there's guaranteed to be a solution. And the reason that that's true is we can actually find it. And so that's what we're going to show you can do. All right. So to get there, we're going to take a little detour here. And we start by asking ourselves a question. What's easy to integrate? Well, the answer's right there. A derivative is easy to integrate. And so since we're solving differential equations, so these equations with derivatives, we say, the favorite thing that we would want to do is say, I see a derivative, because then life is good. Integration, everything works out nicely. Okay, so with this in mind, there's a strategy. It says, hey, you already see a derivative in that y prime part. Maybe this whole left-hand side, it could look like a derivative. And so that's the overarching theme. So sort of to give a sense of where we're going, we're going to do some exercises here. So there's this example. We'll just follow it through. There's parts A, B, C. We'll do in order. So the first part, part A. What's the derivative of x squared y? And here, as a reminder, it says think of y as being a function of x. So how do you take the derivative of x squared y? What's your rule? Well, there is a sort of a hidden chain rule, because y is a function of x. What else do you need? If it helps, there's a product of two functions. Product rule. All right, good. You picked up on my subtle clue there. All right. So if we're taking the derivative of x squared y, well, we can leave the first term alone. It would be x squared, and times it by the derivative of the second term. What's the derivative of y with respect to x? dy dx. We can also write that as y prime. Plus, now I'll take the derivative of the first term, 2x, and I'll leave the second term alone. So the derivative of x squared y is x squared y prime plus 2xy. All right, that's the whole part A. Okay. Well, then we go to part B. Part B says, well, let's find y, given that we have x squared y prime plus 2xy is equal to 5 halves x to the 3 halves. And y of 1 equals 2. Okay, so we look at this and say, have we seen anything like this before? That x squared y prime plus 2xy. It seems like we've seen that somewhere. Have we seen it anywhere before? Part A! Exactly, it's right there! Right there! Oh my goodness, wow. Okay, so we say, wait a second, this left-hand side, it's the derivative of x squared y. And that equals 5/2 x to 3/2. And now we say, well, let's integrate both sides. So we say integrate. What's the integral of the derivative?
X squared y.
The integral of the derivative is what you started with, x squared y. Essentially, you can think of these as undoing one another. Now, there's, of course, a subtlety. There's a constant floating around, the c somewhere. We'll put that on the other side. What about the integral of 5/2 x to the 3/2? Well, 5/2. How do you integrate x to the 3/2? We'll throw some dx's in here. It's going to be x to what power? 5/2, because you add 3/2 plus 1. And then what do you have to multiply by something? 2/5. You know, it's almost like they anticipated our needs. And so that it works out nicely. Is there anything else? Plus c. Okay? And so finally, if I want to get y by itself, we divide by x squared. X to the 5/2 divided by x squared. X to the 1/2. A constant c divided by x squared. You can say c divided by x squared, yeah. Or if you want, you could write as c x to minus 2. Both are fine. So we'll box that. Oh, wait, we weren't going to box that. We'll just squiggly line it, because that's an intermediate step. See, squiggly line just means it's intermediate. What else do we need? We have some initial conditions. Okay, so we have that 2, because I'm plugging in y is 2. 1 to the 1/2 is 1, plus c, 1 to the minus 2 power, 1. So what is c? C is 1. Okay, so we'll put here as part B continued. And so our real answer, because I forgot that there's an initial condition here, x to 1/2 plus x to minus 2. Okay, good. Now I know what you're thinking. There's still part C left, Steve. And you've left yourself no space. It's not true. I have space. Right there. That's all the space I need. Part C. And now a similar problem. Find y given that xy prime plus 2y is equal to 5/2 x to the 1/2, and that y of 1 equals 2. Okay, so I'm just copying this down. And now we ask ourselves the question, why did Steve leave a suspicious gap? No, that's not our question. Is this anything like what we've done before?
Yeah.
Someone said, yeah. If it is, what is it similar to?
Part B.
It's very similar to part B. What's the difference?
Divided by x.
Yeah, there's a factor of x difference. So what can we do? Well, we'll just multiply everything by an x. It's the same equation. Just multiply through by x. And then we say, aha, we already did the work. We're not going to repeat it. Okay. So the moral of this is we said, hey, when we saw that this was a derivative, it made solving part B simple because integrating a derivative is easy. And in part C, we said, oh, by modifying it, by adding an extra part, in this case, multiplying everything through by an x, it transformed it to something where I had a derivative. That's the philosophy. Multiply through by just the right thing so that it's a beautiful expression on the left-hand side. That's what we want to do. Okay. All right. So here we go. The question is, how do we find what to multiply by? It's not so clear, is it? Because you're like, well, there's choices. There's lots of things. Here we knew it because we kind of were following a process, but how do we find it in general? So that's this next part. So we're looking for what's called an integrating factor. So the integrating factor is what makes this left-hand side look like a derivative. That's what we mean by the integrating factor. So it's some function. And so this is it looks kind of like a p, but this is our chance to flex our Greek letters. It's a rho. But that's all right. If you want to think of it as little p of x, that's fine. We'll call it rho of x. So the idea is we're going to multiply everything by rho of x. That's what we want. And then say, okay, this left-hand side is the derivative. In fact, it's the derivative of rho of x times y. That's what we want. That's our goal. Now we're trying to figure out what the right rho of x is. So we think to ourselves and say, okay, if indeed this were to be rho of x times y, and take the derivative of it, we say, well, what would have to be true? We go through the steps we did before. We say, take the product rule. All right, the first times the derivative of the second plus the derivative of the first times the second. So that's the derivative of rho of x times y. On the other hand, we say, but in fact, this is what we have, rho of xy prime plus rho of x p of xy. And then we do the great thing which is called matching. We say, aha, we need these pieces to match. So rho prime of x needs to match up with rho of x times p of x. Well, now that we know that, we start cleaning things up. We move the rho of x across, so you get rho prime of x over rho of x equals p of x. And then we integrate. Say, all right. And the nice thing here is that this integral is very straightforward. Because you have a function downstairs, but the derivative of the function is upstairs. So if you think of the denominator here as being your u, then rho prime of x dx is your du. So that we have the log of u. So that's how we get this log of rho of x. That equals the integral of p of x dx. And so finally, we just want to get rho of x outside the log. So we say rho of x is the exponential function of the integral of p of x dx. So that's how you find just the right thing to multiply by. Now, for all you integral nuts out there, well, integral fans I should say, what have I omitted here? The plus c. I didn't include that. Am I okay omitting the plus c?
Yes.
Yes, good, all right. Because I did it, right? So if I wrote it down, probably it's okay. I just want to assure you that we're omitting it for a particular reason, in that it doesn't help you. If we follow what we've been doing before, when we take our e to both sides, this plus c would become like a new constant in the front. Yes? E to the constant is a constant. We went through and did things like this last time. Now, the moral is, if I throw a constant on each term, what can I then do? I can divide out by the constant, and therefore it doesn't make any difference. And so that's why we don't need to worry about a plus c. It just doesn't make any difference at all. And since we don't need to worry about a plus c, we pick the easiest c that we can pick, which is 0. 0, our old friend. All right, so here's a summary. So this is how we solve problems, linear first-order differential equations. Linear first-order differential. All right. So you rewrite as y prime plus p of xy equals q of x. Make sure it's in the right form. And so the reason we're saying this is sometimes what's in front of the y prime is not 1. There might be a piece of a function here, might be a number here. Make sure whatever is here is a 1. Okay. After we've done that, the next thing is to say, all right, whatever's in front of the y term, this p of x, we're going to integrate that. And then after we integrate that, take e to that function. That is our multiplying factor, rho of x. Once we have that, we multiply both sides by rho of x. And the left-hand side is nice. It's a derivative of something, specifically rho of xy. The right-hand side is, it is what it is. Okay. It might not be so nice. And now that we have our derivative, we're saying we're happy because we know how to integrate derivatives. We integrate both sides. Integral of the derivative is just rho of xy. Integral of this side is whatever it is, plus c. And then, if you want to get y by itself, divide by rho of x. Now, some people might say, okay, I'll just memorize this formula. I strongly discourage you to do that. So learn the process. Don't learn the formula, because the formula can be a little bit confusing to remember. The process is more straightforward. So the process, again, get y prime by itself, grab that p of x, integrate it, e to that, multiply everything through by whatever you just found, and integrate, and clean up. All right, well, that's the idea. So we should try a problem. Is there any question before we try a problem? And we'll have lots of questions afterwards. So many questions. So many questions. All right. All right. Cool. Cool. My goodness, there's tons of questions here. This is exciting. All right, well, we'll start with this one. Okay. Find the general solution for the differential equation x squared plus 1 times y prime plus 3xy equals 6x. Okay, so first off, is this the right kind of differential equation? In other words, is it a linear first-order differential equation? Yes. Something times y prime plus something times x, where the somethings don't depend on y or y prime. And they can be functions of x's, that's fine. Okay, so that's good. What's the next thing we need to do? Now that we know what kind of problem it is, what comes next? Rewrite it. So we need to do what? Yeah, divide by what's in front of that y prime. Okay, so y prime plus 3x over x squared plus 1 times y is equal to 6x over x squared plus 1. Everything gets divided by x squared plus 1. Not just like one term or two terms. All the terms. All right. Good. Now, at this stage, we say focus on this part in front of the y. The 3x over x squared plus 1. All right, this part is the key. We're going to integrate that. So, what's the integral of 3x over x squared plus 1?
ln x squared plus 1.
Someone's doing it really fast in their head. Okay. What's the technique we need to use? Use substitution. Okay. So there's u, the denominator. What is du? 2x dx. Well, we don't have a 2, we have a 3. But that's okay. So first off, I'll put this over as a half du equals x dx. And now we say, well, what do we have? Well, we have that 3 still. The x dx is a half du, and the x squared plus 1 is a u. So 3 times a half du over u. All right, well, that's 3 halves. Integral of du over u, ln of u. And this is the part where we don't have to worry about the plus c. If you wanted to make life harder on yourself, you could. But remember, we love ourselves. Do just the right amount of work. No more. All right? So, we're almost there. So 3 halves, natural log x squared plus 1. Okay, now this is not our integrating factor. Remember, what's going to happen is we're actually going to take e to that. So we want to multiply both sides by e to the 3 halves log x squared plus 1. So this part is our row of x. But we want to try to rewrite that in a nicer way. Is there a cleaner way to write this?
X squared plus 1 to the 3 halves.
Okay, so first off, a constant in front of the log, you can take it upstairs. So this is the same as e to the log of x squared plus 1 to the 3 halves power. And then e and log, they undo each other. So you get x squared plus 1 to the 3 halves. So this part right here is what we would call row of x. We found our integrating factor. And then we say this is the part that's just right. Just right. Okay. Now, we come up and we update our differential equation. The way we update it is everything gets multiplied by our row of x. So, we have an x squared plus 1 to the 3 halves y prime plus, on this term, what's going to happen? We're going to have x squared plus 1 to the 3 halves divided by x squared plus 1. X squared plus 1 to the 1 half. Because we have 3 halves, and this is a 1 downstairs, so you take 3 halves, subtract 1. That's times y. Equals, on the other side, we'll have 6x, and it'll again be x squared plus 1 to the 1 half. Okay. Now, this may not look all that great initially, but we already know what's happening with the right-hand side. This right-hand side is the derivative of what?
Row of xy.
Yeah, it's the derivative of your integrating factor. So that's x squared plus 1 to the 3 halves times y. It always has to be this. And you can double check, you know. The first times the derivative of the second, yep, that works out. And then take the derivative of the first, okay, the 3 halves comes down. It'd be x squared plus 1 to the 1 half, yep, that's right, times 2x. And 3 halves times 2x gives us 3x times y, yeah. So this will always be whatever your integrating factor is times y. And you can double check here. You see, it's nice to check to say, oh, is this right? Or is it not right? So, and then the other side is what it is. All right. So we've had it cleaned up, and now we integrate. That's our next step in the process. The left-hand side, what will this become? x squared plus 1 to the 3 halves times y. I should throw some dx's in here to be precise, because it's easy to integrate a derivative. All right, what about the right-hand side? Can we do that? Give ourselves some space down here. 6x x squared plus 1 to the 1/2. Someone was like, integrate by parts. And probably someone else is like, trig substitution. And then someone else is, I love myself. I'll do u sub. Yeah, don't use a hard tool if an easy tool works. I mean, you can, but don't do it. Be smart. Don't start. All right, so u equals x squared plus 1. What is du? 2x dx. And very conveniently here, well, we have 6x, so we can make that a 3 du. And then we have x squared plus 1 to the 1/2 will become u to the 1/2. All right, well, what's the integral of u to the 1/2? U to what power? U to the 3 halves, all right, because you add 1 plus a half. And in front? 2/3. And it's like they knew we were coming so that we could cancel stuff out. Anything else we need to add? Plus the c, yeah. And so this really becomes 2x squared plus 1 to the 3 halves plus c. All right, so updating over here, the integral of the right-hand side, well, we could just copy it. 2x squared plus 1 to the 3 halves plus c. And now, if we want to solve for y, divide by the part in front. So what do we get for y? 2. Because the x squared plus 1 and 3 halves cancel. And some constant c times x squared plus 1 to the negative 3 halves. And we're done. We're done. This might look slightly similar to one of the problems that you would have on this week's quiz, in that it is highly similar, except on the quiz you just have to verify. Here, we said, look, verify, that's for rookies. We can do it. We can solve it. We don't need to have it. All right. The next problem. Solve xy prime equals 2y plus x cubed cosine of x. All right, well, I did get one of these too. So let's see if we can do it. We'll go through it at a bit of a pace here because there's another thing we want to do. So the first thing is just to sort of rewrite it. So I'm going to do it in 2 steps. I'll move it so the 2y term is on the other side. So subtract. And then I'll divide by the x so that I have a coefficient of 1 with the y prime. So y prime minus 2 over xy is x squared cosine of x. Okay. And then we say, aha, this piece, this minus 2 over x, that's that coefficient of y. Don't forget the minus. That's important. So our integrating factor is the e to the integral p of x dx. But let's do our integration part here first. We'll do the integral of minus 2 over x dx. What does this function turn out to be? Or sorry, what does this integral turn out to be? So minus 2 natural log of x. Or anticipating that we're going to take it to e to that, log of x to the power minus 2. So that says our integrating factor rho, which is e to the log of x to the minus 2, is x to the minus 2, or if you like, 1 over x squared. So the idea is we're going to come up to this equation and multiply everything by 1 over x squared. Everything gets multiplied by our integrating factor. So updating, we will get 1 over x squared y prime minus 2 over x cubed y equals cosine x. Oh, ha, ha, phew. No integration by parts on that right-hand side. Dodged a bullet on that. All right. Well, left-hand side. This is the derivative of something. It's the derivative of what? Rho of x, 1 over x squared times y. And again, you can always double check that it works. All right, equals cosine of x. And now we're like, hey, this will be something we could take an integral of. And so we integrate. We integrate both sides. Integral of the derivative of 1 over x squared times y. 1 over x squared times y. And this, I think, is the part where we have to figure out the difference. The integral of cosine, is it a positive sign or is it negative sign? Positive? Are you sure? Really? Yeah, you are. It's right. I just want to make sure, you know, I don't want you to don't want you to just follow the hype. Anything else we need here? Plus c. And then the last thing to do, multiply everything by x squared. So we have x squared sine of x plus c x squared. So yep, that was close. This one was close. We would have gotten some good partial credit. So, all right. Of course, if in doubt, you would just double check your integral table. It's available to you when you're having the quiz or the exam. All right, good. Well, I mean, it's a process, right? You learn the process, life is good. So now, one of our favorite things, words. Okay. All right. Well, a 120-gallon tank initially contains 90 pounds of salt dissolved in 90 gallons of water. And brine. Now, if you hear the word brine in a problem, think salt water. That's what it means. It means water with salt. So brine containing 2 pounds a gallon of salt flows into the tank at a rate of 4 gallons per minute. And the well-stirred mixture flows out of the tank at a rate of 3 gallons per minute. So the question, how much salt does the tank contain when it is full? All right. Well, what should we do? It's not a test, so we can't go to the next problem. So that's out. So maybe we can draw a picture. So here's a tank. You can tell it's a tank because I just wrote the word tank next to it. All right. And it has 120 gallons. All right. But in addition, there's actually two things happening. Something is coming in, and then something is going out. And so we just need to understand the in and the out. So in the in, we have 4 gallons per minute. And how much salt is there? Well, let's actually figure it out. It's coming in at 4 gallons per minute. For each gallon, there's 2 pounds of salt. So how much salt is coming in? Yeah, so there's 8 pounds of salt per minute. That's the rate it's coming in. Now, inside this tank, there's mixture, and it's swirling around and mixing up really well, and then it comes out. The rate at which it comes out is 3 gallons per minute. So if you're wondering where are all these numbers coming from, they're coming from here. All right. So that's our basic diagram. Now, How much salt is leaving in a given minute?
That's going to be changing. Right?
Yeah, tricky. Yeah, we don't know it yet. That's part of the problem. We get to figure it out. This is going to be fun. All right. Now, let's think about a couple things that are happening. Our inflow versus our outflow. What do you notice?
Inflow is constant, outflow is not.
Sorry, what? So the total amount's going up, right? Because there's more coming in than going out. So I'm just talking about total amount. So eventually we're going to fill up. So it started off at 90 gallons at time 0. How many gallons will you have after, say, 5 minutes? 95, because there's, for every minute you get another gallon. After 10 minutes, 100. After 30 minutes, 120. After an hour, you're still at 120, because it only has 120. You know, it's overflowing after that. But the point here is that we say, look, our amount of fluid, which is the brine, in the tank, is 90 plus T. And this is up to T equals 30. So the real thing is, the question says, how much is there when it's full? It says, what's happening at time 30? All right. So we're after the salt. I know we are, because it asks us how much salt is there. Let's come up with a variable for salt. What do you want to call it? S. All right, this will in no way confuse us. Okay, so S equals amount of salt in the tank. In fact, we're going to say S of T, because it depends on time. All right, do we know what S of 0 is? 90. Yeah, we'll say 90 pounds. We won't worry about units after this point. So initially there's 90. But now the thing is, some salt is coming in, some salt is going out. It's like things are changing. And if we have things which are changing, what should we be using? Derivatives, like a differential equation. Yeah, so that's why we get to talk about this in our class. So that we can talk about the change of the salt. Now here is this cool idea. If I want to know how much salt is changing, what I do is I add the salt coming in, and then I subtract the salt going out. Because salt can't spontaneously generate. It's not as if all of a sudden the water becomes salty. It had to come from someplace. Nor does it automatically go away. It had to go someplace. So if I want to understand the change, I said, well, the only way it can change is either it's coming in or it's going out. So we have two terms we have to figure out. What is our coming in? That might be the easier one. How much salt is coming in? 8 pounds per minute. So what we can say is that this is 8. All right, that's the easy one. It's coming in at a constant rate. It's always coming in at 8. Now, salt going out. Ooh, this one's going to be more interesting. More interesting. So, how much salt is going out? Well, let's change it and ask a different question. How much of the total fluid is going out? Like, what portion of the fluid is going out? Well, 3 gallons is the amount, but I'm looking for the proportion. Like, if I was like doing like a percentage kind of thing, what would I do? Well, how do you find the proportion leaving? Like, you find how much is leaving, and you divide it by by the total. How much is there? So if I'm looking for the proportion that's leaving, how much leaves, how much is there? Now, how much leaves? 3. How many gallons is there in the tank? 90 plus T, because it depends on the time. So 90 plus T. Now, this is just the proportion of the total fluid. But there's this phrase here, well stirred, which means that really we should say it's not just like 3 over 90 plus T of the fluid, it's like 3 over 90 plus T of whatever it is that you're measuring. In particular, it's 3 over 90 plus T, that proportion of the salt left. So that's an S. So it's the proportion of how much of everything left, and say, well, look, salt is part of the everything, so that's how much of the salt had to leave. So we get this differential equation. S prime is equal to 8 minus 3 over 90 plus T times S. All right, now we only have like a minute of class left, so we probably won't be able to finish this problem. But what kind of problem do we have here? It's a linear first order. It's the type of problem we've been talking about. So the same technique can be used to solve it. Move the 3 over 90 plus T across, find the integrating factor, and work it out. All right, well, I guess we'll stop here and pick up again next time on an action-packed day. So make sure to come.